Okay, so summarizing what we've seen and where we are, I've added a couple of things to the picture here. We're going to measure beta clockwise from the negative vertical direction, clockwise from the direction of the vector, the r vector, when the when the mass is at its equilibrium position, but just clockwise in this direction, so that if beta is in this direction, if r is in this direction, beta is positive and sine beta is positive. And if r is over here, which happens, of course, if the wheel rotates around like this, then beta is going to be negative, and the sine of beta is then clearly going to be negative. This is going to take care of the problem of plus and minus signs. Okay, now, what is the net torque then? We know what the magnitude of the net torque is. Well, if beta is positive, it's because the mass is out here. And if the mass is out here, then the r cross mg is going to be this cross this. It's going to be back into the board. And that's going to be what? That's going to be the negative z direction. If this is the x direction and this is the y direction, which is how we decide to, we might decide to do it, then the cross product is going to be in this direction. The z direction is going to be out of the board. So if the x direction is here and the positive y direction is here, the z direction is out of the board, but the torque is into the board. Okay, well, the unit vector in the z direction is the k vector. It follows then that the net torque is going to have magnitude r, big R mg sine beta, but if beta is positive, so that sine beta is positive, the net torque has to be in the negative k direction. That's going to be like this. That's going to make this a restoring torque, a torque that restores the position, tends to restore the position to the equilibrium position. In that case then, our angular acceleration, net torque divided by I, is just going to be then negative r mg sine beta, same expression that we got here originally, divided by the moment of inertia, times k. The negative sign and the k come from incorporating the direction by declaring that beta is positive if measured in the counterclockwise direction from the vertical. Okay, in any case, we've got an equation for alpha. How do we get the equation for beta? So beta of t is going to be your position function. How do we get the position function? Well, alpha equals tau net over I equals all this, okay? Also, alpha is the second derivative of your beta function. Second derivative with respect to time of your position function. So this equation becomes this, and that's multiplied by our k vector. Well, the k vector is just kind of a constant, so we're going to kind of ignore that, and then we'll reintroduce it. But how do we solve this equation? Well, this equation is of the form theta double prime equals negative I'm going to say mgr over I sine beta, and also for small angles beta, because remember, we're assuming this is a small distance here, which will make the angle beta small. The angle beta, the sine of the angle beta is just close to the angle beta. So we're going to be able to do what we see over here. Okay, this kind of repeats what we've got here. Tau is I omega, so alpha is tau divided by I, which is this expression, which we've just written down. And then small beta implies that sine of beta is approximately equal to beta. So we're going to get beta double prime equals negative mg r over I times beta times k. And that's the differential equation that we already know how to solve, because we solved an equation of exactly the same form in developing the equation of simple harmonic motion for an object moving back and forth as opposed to rotating. So we'll continue with that momentarily.